Dear student, in my first lecture, just you have seen that how classical mechanics fails to explain the black body radiations. Now, I will focus your attention on the second phenomena, that is the photoelectric effect. So, we have to see here, that is how classical mechanics fails to explain the photoelectric effects and what are the facts about the photoelectric effect. Just look towards this figure here. They are the metal plates called as the emitter plates, and this is the collector plates. So one is the emitter plate, another is the collector plate. So emitter and collector plates are just joined together through the battery, and ammeter is used for indications of the current flow. So what will happen here, if you look it very carefully, this is the incident radiations. So if the incident radiations of the suitable frequency is incident on this emitter plate, I repeat once again, if the incident radiations of the suitable frequency is strike here, if it is incident on the emitter plate, then from the emitter plate, the electrons are emitted. These emitted electrons is known as the photons. But what is the condition? What is the fact about this photoelectric effect? Electrons from this metal surface emits only when the frequency of this incident radiation is greater than or equal to the threshold frequency. So if this condition is not followed, if does not follow this condition, then no photoelectric emission will be absorbed. And therefore, what are the facts? Before going to the discussions on this classical mechanics and the quantum mechanics, let us see the fact. So first fact is that electrons are ejected only if the frequency of incident radiations is greater than or equal to threshold frequency. That means if the frequency of incident radiation is less than the threshold frequency, no photoelectric emission will be observed. So for emissions of the photoelectrons, the first condition is that intense frequency of the incident radiation, these radiations, okay. So frequency of the incident radiation must be greater than or equal to threshold frequency. Second fact about the photoelectric effect is that this is an instantaneous process. That means there is no time lag between the incidence of the light on the metal surface and the ejections of the electron. That means as soon as this incident radiation is incident on this metal plate, immediately there is a emissions of the electron. So this is an instantaneous process. There is no at all time lag between the incidence of the light and the ejections of the electrons. Okay. Third fact about this photoelectric effect is that kinetic energy of the ejected electrons depends upon the frequency of the radiations. So this kinetic energy of the ejected photoelectrons, so these are the photoelectrons which is ejected from this emitter plates. If you apply a light of suitable frequency, so what about the kinetic energy? So kinetic energy of this, look towards this my cursor, okay. So this kinetic energy of this ejected electrons depends upon the frequency of incident radiations, and the number of electrons ejected depends upon intensity of incident radiation, provided that the first condition is followed. So very important thing about the fact number 4 is that number of photoelectrons ejected. Here, how many number of the photoelectron will be ejected, that depends upon the intensity of incident radiation. But the initial thing, basic condition is that the frequency of incident radiation must be greater than or equal to the threshold frequency. Okay, if this condition is followed, and if you increase the intensity of the incident radiation, then and only then the number of ejections of the photoelectron will be increased. So this is the fact about the photoelectric effects. I repeat once again. Number 1, electrons are ejected only if the frequency of incident radiations is greater than or equal to the threshold frequency. Second fact, no time lag between incidence of the light and the ejections of the electron. Number 3, kinetic energy of ejected electrons depends upon frequency of incident radiations. And the last fact about the photoelectric effect is that number of electrons ejected depends upon intensity of incident radiation, provided that first condition is followed. Now see here, this figure is more explanatory. See, this is what the potassium metals, whose threshold frequency is 2.0 electron volt. So, you know that E equal to h nu, that is the frequency is directly proportional to the energy. So this figure is given in the form of the energies. Okay. So let us see here, but by before looking this figure, so you should have to keep one things in your mind, that the frequency is directly proportional to energy. Here these figures are given in the form of the energy, that's why I am telling to you. Okay. So here see, this is the potassium metal, and here the 2 electron volt is needed for the ejection of the electron. Now, if you incident the radiations having 700 nanometers, so 700 nanometer is the wavelength, and the corresponding energy of 700 nanometer wavelength is 1.77 electron volt. See here, what you need, if you incident the radiations whose energy is 2.0 electron volt, then and only then the ejections of the electron from this metal surface will be observed. So, but if you strike the incident radiations having the wavelength 700 nanometer, whose energy is 1.77 electron volt, so you will find that no electrons are emitted, no ejections of the electron. Why there is no ejections of the electron? Because we are supplying the incident radiations whose frequency is less than that of the threshold frequency. But let us see the next part. Okay, here you are having 550 nanometer wavelength, but the energy is 2.25 electron volt. So what is the minimum energy required for the ejections of the electron? It is 2.0 volt, and you are supplying the wavelength whose energy is 2.25. That means 2.25 electron volt energy is greater than 2 electron volt energy. That means you are supplying the maximum amount of the energy than the required, and that's why there is a emission of the electron. See here, what there is a emission of the electron. Okay. Now see the third fact. Here, if you supply 400 nanometer, if you incident the light of 400 nanometer wavelength whose energy is 3.1 electron volt. So required energy is only 2 electron volt, but you are supplying the energy in the form of the light is 3.1 electron volt. So it is more than the first case, second case, right? In first case the energy was 1.7 electron volt, that's why there will be no ejections of the electrons. But in second case you had supplied 2.25 electron volts energy, and that's why there is a ejection of the electron. In third case you incident 400 nanometer in 400 nanometer wavelength having the corresponding energy 3.1 electron volt. So definitely 3.1 electron volt energy is too much greater than the 2 electron volt energy, and that's why more and more number of the electrons are emitted. See here Vmax value. Here in earlier case, in case number 2, 2.96 into 10 raised to power 5 meter per second, and here the value is 6.22 into 10 raised to power 5. So definitely here 2.96 into 10 raised to power 5 is less, whereas if you supply more and more number of the energy, so Vmax is maximum. Okay. So here what? Classically, for light as a wave, its energy is proportional to square of the amplitude. So from this figure, it is very clear that the ejections of the photoelectrons from the metal surface is possible only when the frequency of incident radiation is greater than or equal to the threshold frequency. So that here what classical mechanics said about the photoelectric effects. What are the things related to the classical mechanics? How classical mechanics considered photoelectric effect? So what classical mechanics considered? According to the classical mechanics, energy of light depends upon the intensity. This is what the assumptions of the classical mechanics. See once again, energy of light depends upon intensity of light and not on the frequency. See the things. Energy of the light depends upon intensity. This is what according to the classical mechanics. Classical mechanics said that energy only depends upon the intensity but does not depends upon the frequency. Second assumption, if the light of sufficiently high intensity is incident on the metal, there should be an emission of the electron irrespective of the frequency. That means frequency has no place while considering the photoelectric effect as per the classical mechanics. So if you look this about the two facts, that is fact number one, energy of the light depends upon the intensity and does not depends upon the frequency. So you know that this is not possible. So energy related to the frequency according to the equation E equal to h nu. And what classical mechanics said that if light of sufficiently high intensity is allowed to incident on the metal surface, there should be the emission of the electron irrespective of the frequency. So if the whether the frequency is low or whether the frequency is high, it doesn't matter. So emission of the photoelectron is possible when the light of sufficiently high intensity is incident on the metal surface. But this is practically this is not possible, and that's why classical mechanics fails to explain photoelectric effect. Why classical mechanics fails to explain the photoelectric effect? The reason is very simple, because the assumptions of classical mechanics is based on the fact that energy of the light depends upon the intensity and does not depends upon the frequency. So this is not possible. Second thing is that if the light of sufficiently high intensity is incident on the metal surface, there should be an emission of the electron irrespective of the frequency. This is also not happen. And because of these two considerations, which is totally found to be the incorrect. So because of these two assumptions which are found to be the incorrect, classical mechanics fails to explain photoelectric effect.